All right. My name is Ralf Haefner, and I want to start the presentation by acknowledging the two talented grad students who led this work, Anton Platanev and Shizao Liu, and of course the CRCNS mechanism that has funded this work. So Helmholtz famously observed, I don't know, over 100 years ago, that the information that the brain receives at any moment in time from the sensory periphery is inadequate to give rise to the rich inferences that the brain is capable of, and that it must somehow be combining those impoverished sensory inputs with prior experience and prior knowledge about the world to support those rich inferences and our rich perceptual experience. So here's a simple example. Any 2D projection on our retina, even if you only have one eye, we perceive as, or we can use to perceive the structure of the three-dimensional world around us. And of course, there are infinitely many different such three-dimensional structures that are compatible with any one projection. And what the brain seems to be doing is making us perceive the most probable explanation for the sensory input. So how does the brain compute this most probable structure, and how do biological neurons and neural networks of neurons support these computations? That's the central question. That's a big question for systems neuroscience, and the central question that's motivating most of the work in my own lab. One cue is provided by this anatomical figure already shown earlier this morning, that when you squint hard enough, can be simplified to the insights that the many areas that make up the visual system are hierarchically organized and bidirectionally connected. So there are feed-forward connections from the retina to V1, and then V1, V2, V4, IT, etc. Are bidirectionally, and of course within each are recurrently connected. And this has been pointed out by Mumford and colleagues again for the past almost like 20 years, more than 20 years, 30 years, that this kind of information flow in cortex is compatible with the idea that the brain performs probabilistic inference in a generative model that it has learned of its sensory inputs. And that, of course, is in contrast to how I would say most people think about sensory processing as an information processing system in which informative features are extracted from the sensory inputs. All information is on the retina. It's just the representations are transformed to make them more useful at every stage, but in a fundamentally feed-forward fashion. So when you one of the outages. So when you now stick an electrode somewhere in the brain and record neural activity and then try to make sense of it, the way that's typically been done is by trying to find an encoding model that relates the external world, the stimulus, to the neural responses, predicts neural responses from the stimulus, and then asks what information in these neural responses allows me to decode the stimulus, encoding, decoding framework fundamentally. And in this framework, has turned out that one of the most important aspects of how well that's possible, how much information there is, are noise correlations, the correlated variability of these sensory neurons. And just to make sure we're all on the same page, here's a simple cartoon that recaps the central findings from many studies of two neurons, neural activities, if they're tuned to a stimulus with their tuning functions that corresponds to a one-dimensional line in this two-dimensional space. Now, when you show even one particular stimulus many times, then cortical neurons are famously variable, and they're not just variable, but they're also correlated. And the variability impairs your ability to distinguish between two, let's say, nearby stimuli. But importantly, and that's even more important in higher dimension than in two, the relationship of these correlations to the tuning function greatly influences how well you can decode. And here the marginal distribution or variability for each of the neurons are the same, but they're simply the only thing that's changed is the correlation. And the upshot of all of this is the key thing that matters is how these correlations in the noise relate to the changes in the mean activity for those neurons. So how they relate are relative to F prime direction, the direction in which the neuronal responses change as a function of the stimulus. Okay, and when they're aligned with F prime, then they are, they make it the hardest, and that's why they've been called information limiting correlations in a paper by Moreno Bote 2014. So it's these differential correlations. I want to stick to the term differential correlations, which kind of form the center of the talk. Okay, so why should we study them? Of course, to understand the information, as I just talked about. But even if you take a step back, correlations between neurons in general can provide important cues into variables inside the brain that may vary, right? Sensory neurons receive inputs not just from the feed-forward, sensory periphery, but also through feedback pathways from elsewhere in the brain. And variability in those, feedback signals, if they are, arriving at multiple neurons, induce correlated variability, and you can use those then, use this correlated variability to infer something about these internal variables. A special case of that, and most relevant for my talk today, is that under the assumption that the brain performs hierarchical probabilistic inference, we can actually make very specific predictions for how those neurocorrelations, those noise correlations, should change over time. And I don't have time to go through the mathematical details of this, but just to give you an intuition here, back to this picture I just introduced, if these two neurons represent posterior beliefs about aspects of the outside world, latent variables, then their activity should not just depend on what's actually on the retina, on the screen, the stimulus, but also on prior expectations in the rest of the brain about what those aspects, those latents, should be. And importantly, one can show that if such a hierarchical probabilistic inference system learns a discrimination task, a 2FC task, distinguishing between two stimuli, as shown here, for instance, then the internal belief about the correct choice, which of the two stimuli it is, will influence sensory neurons in the same way the external stimulus influences them. So mathematically written, the derivative of the tuning curve with respect to the internal belief about the correct choice, that's a binary belief, is proportional to the direction in which the tuning changes due to the stimulus. Such that, as a result, trial-to-trial changes in the internal belief about the correct choice, even if you keep the stimulus fixed, will induce extra variability in the direction of F prime, so-called differential correlations. And the striking and seemingly paradoxical prediction from that finding is that as a system, or as the hierarchical, as the brain learns this task, those differential correlations should increase. So those correlations that are most harmful for representing a stimulus should increase while the performance of the animal gets better. Okay, and of course that's in complete contradiction to what the classic feed-forward view would propose, where if you're strictly straightforward, then you would say maybe information limiting correlation shouldn't change because they simply reflect a limited input information, or maybe at best over long times due to perceptual learning, etc. You might expect that they even decrease, right? And that decrease leads to higher information in population, and that's what then supports improved sensory performance, or improved performance in the task. Okay. So we'll study, measure these correlations, and test this prediction. Okay, so we've designed a simple 2FC task that the monkey can do based on prior studies. Monkey fixates, two targets are up, then the stimulus appears in the periphery, and the monkey at the end has to make a saccade to which of the two targets, to the target corresponding to their percept. We train the monkeys on two different tasks: a cardinal task, vertical versus horizontal, and oblique task, -45 + 45. And corresponding to different target locations, different target colors, and the correct targets come up first, or the targets corresponding to the correct task. So the monkey, always knows which task to do. Here the stimulus, again based on prior works, bandpass filtered, Gaussian noise, oriented, where we can vary the coherence to make the task easy or hard. For the cardinal task and for the oblique task. Okay, so here's the timeline. First, we train the monkey on the cardinal task, so only cardinal task, then the oblique task, and then both tasks interleaved. At the end of cardinal training, we implant an array, Utah array in area V4, and start recording. And the key period here is the period of learning the oblique task, where we have the entire period from the beginning of learning to the end of learning. And this is the central empirical result that the differential correlations increase over the course of learning. They are indistinguishable from zero, at least our signal to noise, and then increase over time. And this we've quantified this in multiple ways. Versus day versus degree of training, and this is a really robust result. Importantly, when we look at the differential correlations in the other direction, like this is the differential correlation with respect to the cardinal task, and in dashed is the differential correlations with respect to the oblique, solid is oblique task, the one that the monkey is learning, and dashed is the cardinal task, the task that the monkey has previously learned. We find there are some significant non-zero correlation at the beginning, but they don't change over the course of training. Okay, now we look at the interleaved period, and what we find is that again, now the monkey is interleaving both trials based on the cues that they see, and again in the cardinal behavior trials, we see these differential correlations for the cardinal direction, oblique for the oblique direction. But interestingly, also in the cardinal behavior trials, we see the differential correlations for the other direction. Somewhat lower for the oblique task, but this difference is not significant. Okay, almost out of time. We also checked, same analysis, that choice probabilities, the correlation between individual neurons and choice, do change, switch on a trial-by-trial basis. Also, confirmed with lots of statistical analyses that the behavior changes, etc. So this is so we're very pretty confident of this. So the main summary here I want to say is that look, the differential correlations increase over learning. That's a real challenge for the classic encoding decoding framework. How most of us think about how to interpret population activity, how to relate it to behavioral performance, what happens during attention. Oh, correlations go up, performance should go down, vice versa. This is the neural basis of learning or of attention or of whatever it is, I think we should really try to move to a hierarchical inference framework. I don't have time to talk about this, but having all these measures at the same time really allows us to more precisely dissociate feed-forward and feedback contributions to the correlational measures like choice probabilities right in the system. Having measured all of this, we can basically now really infer causally, which is changing over time over learning and interleaved. The feed-forward pathway from the retina, the feed-forward from sensory decision-making areas or decision-making areas back to sensory areas. Okay, I do want to take just a few seconds to say that, look, we're actually kind of at the end of our grant. We only have one monkey. What happened? Well, all of this is really based, standing on the shoulders of the work by Richard Lang and Camille Gomez-Laberge, who did this very same project first in area V1. And in area V1, maybe not surprising with hindsight, the top-down signals that we were set out to measure were simply too weak for us to draw robust inferences on, leading to a painful process of writing it up. But now we're repeating all these measures in V4, and as expected and hoped, we have stronger signals. Okay, I want to thank all the members of my lab, all the funding sources, and you. Thank you.
Thank you, Ralf. Have time for questions? Yes.
Thank you for the talk. So when you calculate the differential correlation, did you only use in correct trial? I'm assuming you only calculated only the correct trial, or when you calculate the statistics?
The way I think about differential correlation is basically the variability of neural responses in a particular direction in neural space. So we can measure that for any trials.
So if you compare correct versus error trial, what would be the differences?
That's a good question. We have not compared correct versus error. What I've compared here is the trials where the monkey was instructed to do the cardinal discrimination task or where the monkey was instructed to oblique discrimination task. But correct and...
So I'm wondering, the reason I'm asking the question is because you say the correlation can increase during the course of the learning. Could that be because it correlates with the number of the correct trial also increase?
Why should that?
Well, because the performance during the course of learning, generally performance improve, but the correlation also increase. So I'm wondering whether the correlation is due to the performance increase. So if you try to, in different sort of, try to compare the correct versus error at different sort of section, will you see a difference?
Okay, again, thanks. I'll think about this. I don't have a good answer.
Okay, so thank you very much, Ralf.